Hello again. We continue with chapter 11 with 11.9, representations of functions as power series. We are looking at familiar functions, and we're going to have a list of functions that are presented as power series. Why? Number one, to represent them as sums of power series. What do we use that for? To integrate functions that do not have elementary derivatives, and also to approximate functions by polynomials. Okay, we do know at least one power series representation of 1 over 1 minus x. We've looked at this a long time ago. And this we know is the sum from n equals 0 to infinity from x to the nth power. And of course, it converges for x less than 1 in absolute value. And we say that this is the power series representation of 1 over 1 minus x. And of course, the interval, as you see here, the domain of this function is negative 1 to 1. Okay, so now our next step would be to go back to power series again. So we have the sum from n equals 0 to infinity from coefficients Cn and x minus a to the nth power. And of course, the domain of this function, like before, like for this one, the domain is the interval of convergence of the series. Interval of convergence of the series. Okay. When we differentiate or integrate a power series, that's a note for us here. When differentiating or integrating power series, the interval of convergence may not be the same. The radius in convergence remains the same. Radius, same. The radius of convergence is the same, but the interval of convergence may not be the same. Of the resulting series. When we differentiate or integrate the power series, we get a new series, and the radius of convergence stays the same, but the interval of convergence may not be the same. Okay, so let's look at a theorem. Let's state that theorem. It's called term-by-term differentiation or integration of power series. Term-by-term integration or differentiation of power series. So assuming we have the following power series, n equals 0 to infinity from, of course, C sub n x minus a to the nth power with a radius of convergence greater than 0, then the function that represents this, that is represented by the power series, n equals 0 to infinity Cn x minus a to nth power, is differentiable, and as we know, if it's differentiable, it has to be continuous, on the interval of convergence, a minus r, a plus r. And then what happens is, number one, we can differentiate. That's number one. And number two, we can integrate. Okay, so let's see what we get. When we differentiate this function in the form of or represented by a power series, the answer would be the sum, careful now because we are losing the first term, from n equals 1 to infinity, from n Cn x minus a to n minus 1, and the radius of convergence stays the same. Or if we integrate, then we will have a constant plus the sum from n equals 0 to infinity from the same coefficients, but of course x minus a to n plus 1, of course, over n plus 1, and the radius of convergence is the same. Okay, so let's look at a few applications and illustrate what we just discussed. So let's start with, we're looking on page, which page am I on? Page 793. Okay, so this is one power series representation for this function. I would like to add two more here that you will see. So please look at page, let me see, page 790 for the following two proofs in examples 5 and 6 on this page. And you will see that natural log of 1 plus x can be represented by the sum from n equals 1, careful, 1 to infinity, from negative 1 to n minus 1, x to the nth power over n, and the radius of convergence is 1. And the one from example 6, that is arc tangent x or tangent inverse, which is the sum from n equals 0 to infinity, from negative 1 to power n, and as x to 2n plus 1 divided by 2n plus 1, and the radius of convergence is still 1. So please look at these two proofs in case you need to see how we got these two results. And they are in the examples 5 and 6, page 790. So we are going to use them when we need them. Okay, that's page 3. Okay, so let's start with number 3, and let's mention 793. So we're given, the question is asking us to find the power series representation for the function and determine the interval of convergence. So we have f of x equals 1 over 1 plus x. So that's one of the reasons why I already reviewed this with you here. So notice the similarity. Very simple to just change this function into 1 over 1 minus a negative x. And then we follow the representation for 1 minus x, which will be the sum from n equals 0 to infinity. But this time we have negative x to the nth power. And of course, we didn't finish, but negative x still has to be less than 1, which means the same thing, which means the radius of convergence is 1. And the interval of convergence is negative 1 to 1. So now, let's finalize this. So we're going to write it as negative 1. I'm going to erase it from there. I don't have enough room. Sorry. So we will separate negative 1 and x to power n. Okay. So we have the sum, negative 1 to power n, x to power n, from n equals 0 to infinity. Okay, moving on to number 7 on the same page. And the question is the same, but we are given f of x equals 2 over 3 minus x. Again, we're trying to use the same procedure because it's the same type of function. So what I'm going to do is I'm going to factor out 3 in the denominator and present the function as 1 over 1 minus x over 3. And then I can continue applying the same procedure we applied for the previous problem. So we have 2/3 in front and the sum from n equals 0 to infinity. But this time we have x divided by 3 to the nth power. We'll continue, but of course we cannot forget this. So that means that the absolute value is less than 3 and means that the radius of convergence is 3 and the interval of convergence is -3 to 3. So let's continue here. So we have the sum from n equals 0 to infinity, x to the nth power. I meant to write x to the nth power. And there is a 2 in front, which is fine. 3 to the nth times 3 will be 3 to n plus first. Okay, moving on to number 9. Same page, 793. And here we have f of x equals x squared over x to the 4th plus 16. Again, the same procedure. We rearrange the function so we can get it ready for the same application. So we have x squared. I will factor out 16. And in parentheses, we have 1 minus. And in parentheses, negative x to the 4th divided by 16. Better use brackets here. One more time, let's check. 16 times 1, positive 16. These two cancel each other. 16 times x over 4th power, x to the 4th power divided by 16 is this. Okay, I will continue on page 4. Okay, so we have an x squared over 16 in front. We have the sum from n equals 0 to infinity. And we have negative x to the 4th over 16 and everything raised to the nth power. Let's see how we simplify all this. And of course, we have negative x to the 4th divided by 16 and absolute value less than 1, or nothing else but negative x over 2 in absolute value less than 1. So the radius of convergence is 2 and the interval is -2 to 2, because this is the same with this. Okay, so let's see how we simplify. We have the sum from n equals 0 to infinity. We have -1 to the nth power. And this is x over 2 to 4n. So x over 2 to 4n and multiplied by x over 2 to the 4th. X squared over 2 to the 4th. Okay, so we simplify with n equals 0 to infinity, -1 to the nth power. So we have x to 4n plus 2. And here we have 2 to 4n plus 4. That's all we needed. And moving on to 21. Same page, 793. And 21, we are asked, find the power series representation for the function and determine the radius of convergence. So we have f of x equals natural log of 5 minus x. So I hope we remember that the natural log of 5 minus x is the same with the integral from 1 over 5 minus x dx. Because when we integrate 1 over 5 minus x, and we have to take care of the negative also because it's negative, see, when we differentiate this, we get 1 over 5 minus x times -1, which is exactly this. Okay, like before, I'm going to factor out 5. So this is -1/5, the integral from 1 over 1 minus x over 5 dx. Now we're going to change this into its corresponding power series representation. So we have -1/5 and the integral from the sum from n equals 0 to infinity from x over 5 to the nth power, of course, dx. And let's see what we have next. So we have negative the integral from the sum n equals 0 to infinity from x to the nth power over 5 to n plus 1 dx. 5 to the n times another 5 to the n plus 1. And finally, we are integrating, and we get c, a constant, minus the sum from n equals 0 to infinity, x to n plus first, over n plus first times 5 to n plus first. Okay, so now what has to happen here, of course, x over 5 in absolute value less than 1, which means the absolute value is less than 5. The radius of convergence is 5. And now let's see what happens if we can determine this constant. So when x is 0, this is 0. 5 minus 0 will be 5, so the constant equals natural log 5. Okay, moving on. The next question, 23. On the same page, 793. Let's see how we are on time. Okay, still good. Okay, 23. Find the power series representation for f and then graph several partial sums. Okay, so f of x equals x squared over x squared plus 1. Again, the same type of function. We are going to rewrite it as x squared over 1 minus negative x squared. And we have x squared, the sum from n equals 0 to infinity, from negative x squared to the nth power. And of course, negative x squared in absolute value less than 1, which means x less than 1, and the radius is 1. Of course, the interval of convergence, negative 1, 1. Okay, so let's clean this up a little bit. So we have the sum, n equals 0 to infinity. We have negative 1 to the nth power, x to 2n plus 2. Okay, now they're asking us to graph, and let's graph s1 equals x squared when n is 0, and then s2 will be x squared minus x to the 4th, and then s3 will be x squared minus x to the 4th plus x to the 6th. S4 will be x squared minus x to the 4th plus x to the 6th minus x to the 8th. And this is good enough. X squared minus x to the 4th plus x to the 6th minus x to the 8th plus x to the 10th. And in order to graph these, I put them in the graphing calculator. So under y equals, I have x squared, minus x to the 4th, and so on and so forth. Of course, the interval of convergence is negative 1, 1. So go back to window. Make sure you have negative 1 to 1 with a scale of 1 and 0, 1, 1. Negative 1, 1, 1, 0, 1, 1. And when you press graph, careful. Here comes the first, which is x squared. The next one, which is a difference. Then the next one, and then the next one, and then the next one. We have 5. Okay. Good. Let's see how we are on time. I'm going to stop here and continue with the next in the second part. Thank you.